Yeah, it was the signs were weird.
And then also mention things
Yeah,
over negative and into it.
I made sure, I
Yeah.
like, I plugged my answers back into the equation. to make sure
I got it, yeah.
But yeah, it was -1.
Okay. I rewrote my book. I just need the last. Thanks. I was still on your numbers. I wouldn't even ask. I wouldn't even expect it. As I wouldn't even ask you, I'll be expecting. Oh, okay. After every class, I'm like, hold up, I'm gonna send it to. Yeah. She. More than my friends, so my mom. I was like, it's really sick around. And
For problem D, the sheet had a less simple form, but I simplified it just so that y-index, is it fine?
Yeah, that's fine.
It's bigger.
and I'm going to. Oh, you need some of the sheet. Who's my you? Oh, oh, yeah.
Yeah. Yeah, there is a mistake. For the surface. This sign. It's like, it's basically almost the same, just with a negative. So-
It's like, you know, it wasn't wrong, it was just like, you know, differently. No, for this one, I'm 17 over 2. That's fine. Oh, yeah, you had no. From. Absolutely. You're right. Where did my thing? No, you did. Yeah, I was only. You just forgot to my name. Yeah. I hate when you review it together.
Oh, yeah.
Are you finding it?
Yes, thank you.
Yeah, you would be stuck.
Yeah, right. You gotta keep that right. Yeah, I know. Just do a little. You're a big high. I wanna do that. So you know that. You gotta do it. You gotta jump on it. We're gonna do it. We're gonna do it. You it's just like the brand. Focus. And still do this.
Yeah.
I don't have to on those. That's just.
Yeah, so it is right.
Oh, yeah. You see it over this.
It's not to use like, you know, as the equator. No sign X times it's the tree, and I was like, I'm not solving. Because the equation for yeah, and it's a really, really long one, and I was like, this.
Yeah.
I had her check my food. Was missing a sign, the gay negative sign. And then, so there was something over to the over to, and I was like, that's what I was like.
This one's okay. But I like that one.
Yeah, I was like, why did they come here?
Oh. All right, it's 4 o'clock. Let's go to get started. All right, good afternoon, everyone. How's everyone doing today? Doing good. All right, so today our first homework is due. So make sure you get that into Canvas. So it is due at 11:59 p.m. tonight. So a couple typos. So there were a couple of typos in my solutions that I had on the homework itself. So I think the main one that a lot of people have been catching is problem 2A. So in problem 2A, I think on the homework sheet, I had this as a -2 times e to the 2x. It should be -1/2 e to the 2x. And that, of course, changes the value of the constant too. So that changes to 17/2 e to the 4. Okay. So make sure you correct that, or maybe stop pulling your hair out if you're not getting the -2 there. And then there's a small typo in problem 3A too. So the cosine term in that solution should be negative. So you make sure you get that as well. Okay, so plan for today is we're going to go, today is just going to be all second order equations. So we're going to go over second order ODEs, constant coefficients. We're going to go over how to solve those. And so we're going to go through learn something called characteristic equation, what that is, where that comes from, and how we use it to solve problems. And then we'll talk about some applications today too. And so second order ODEs most popularly are used to analyze mass spring damper systems and electric circuits. And you know, even though mass spring damper, you've probably seen a mass spring damper at some point before this class, but you'll see that mass spring dampers are actually very versatile, and they actually model the behavior of a lot of physical systems. And so, you know, understanding second order ODEs, the different types of solutions, the behaviors of the solutions, and its application to mass spring dampers will actually, you know, that gets you, you know, most applications or second order ODEs that are out there. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. Okay, so topic today is second order ODEs. So last time we were here on Tuesday, we finished up talking about first order ODEs. First order being that the highest order derivative in the equation is 1. But now we're on the second order, which means that the highest order derivative is 2. Okay. So we kind of very briefly introduced the concepts last Tuesday. So let's just kind of summarize the key points. Okay. Okay, so the first point that we went over last time was that for a second order ODE, we are always going to get 2 solutions. Okay. In particular, we're going to get 2 solutions to what we call the homogeneous problem, right? So the homogeneous problem basically means that the right-hand side of the equation is equal to 0. Okay. So just to kind of refresh your memory, a second order equation looks like the following. So you have d squared y dx squared plus p p dy dx plus qy. Okay. A homogeneous problem means that the right-hand side of the equal sign here, basically any term that doesn't have y or its derivative multiplied is going to be 0. Okay. So that's what it means to be a homogeneous problem. Is that there's no term in the equation that does not multiply by y or one of its derivatives. Okay. We're going to go over inhomogeneous problems or non-homogeneous problems probably next week. I don't think we're going to get to it today. That's something that we need some additional techniques to do. But for now, we're just going to focus on the homogeneous problem, and you're always going to get 2 solutions to that. Okay. The other thing that we discussed is that the 2 solutions that you do get to the homogeneous problem have to be linearly independent. Okay. And so linearly independent, what that means is that basically what it means is that your 2 solutions have to have different functional forms. In other words, you just can't simply add them together and combine them into one term. Okay. So, at the end of class on Tuesday, we went over some examples of, what's considered linearly independent and what's considered linearly dependent. Okay. So I'll kind of flash it on the screen just for a second, just to kind of remind you. But, this is the example that we talked about. So, if we look at x and 4x squared, these are independent because they are different functions of x. If we look at 7x and 4x, those are not linearly independent because you can combine them together to form 11x. Okay. And then finally, we have e to the 4x, e to the 7x. These are linearly independent because, if you have different exponents, even though they're both e terms, you can't just simply add them together. So e to the 4x plus e to the 7x, those cannot combine at all. Okay. So those are our requirements for a second order ODE. 1, you have to get 2 solutions, and 2, those 2 solutions have to be linearly independent. Okay. But now, of course, this begs the question of, how do we even obtain these solutions to begin with? So we know how many they are. We know some characteristics about those solutions, but how do we actually start to solve these? Okay. It turns out second order equations are very difficult to solve by themselves. And so, the only class of equations that we're going to solve is actually a very specific, subset of these equations. And so, we only really have good techniques to solve second order ODEs when the coefficients are constant. Back when we were doing first order ODEs, we didn't have this constraint. So in first order ODEs, our coefficients could be functions of x, and we can deal with those just fine. So we can do separation of variables, we can do integrating factor. Both of those techniques work for non-constant coefficients. For second order equations, we have to be a bit more restricted. So we can only look at cases where the coefficients are constant. Okay. And so we come back up to the form here. And so let me let me highlight the coefficients for you. Okay. So the coefficients here are P and Q, okay? So our solution techniques only work for when P or Q are just constant numbers. Okay. Okay. And so if you want to classify the types of problems that we can actually solve by hand, these are second order linear ordinary differential equations with constant coefficients. Not a very catchy name at all. And so, just by shorthand, from here on out, I'm just going to call them second order ODEs. But just know that they, one, have to be linear, and two, the coefficients have to be constant. Okay. So now that we have that constraint out of the way, so now that we know that we're looking at equations where the coefficients are constant, let's come up with a technique to do this. Okay. So the way that we actually solve these equations is to make use of what's called the characteristic equation. The characteristic equation is a polynomial equation that represents the ODE in question. And the roots of that characteristic equation are going to be used to form our two linearly independent solutions. Right, so in particular, the characteristic equation, because we're doing second order ODEs, it's going to be a quadratic equation. And so the roots of that characteristic equation are what we're going to do. Okay. So if you haven't used it in a while, dust off your quadratic equation because we are going to use it. Okay. Quadratic formula. I think there's a song that people use to remember it. Don't ask me to sing it. That is a step too far. Usually I'm very open, but trying to sing in front of a group of people is not one of my not one of my talents. So okay. So how do we do this? And so let me write out the equation again. Okay, and once again, we're looking at the homogeneous problem, so the right-hand side is equal to 0. So when we look at this, we look at this and say, even with constant coefficients, a method for solving this doesn't immediately jump out. One thing that would help is that, it would help if we knew or we had some hints about what form or what functional form the solution would look like. Okay. And so for inspiration, okay, let's look at an analogous case for a first order equation. So let's look at a first order differential equation with a constant coefficient, and let's see what that solution is going to look like. Okay. So first order equation, we'll say is dy dx plus py is equal to 0. Okay. So this is kind of a subset of the equation that we solved for before, right? Except we're even more restricted in this case because we know that p here is going to be constant. Okay, so let's solve this. And so even though P is just a generic constant here, we can actually solve for its solution. So let's use separation of variables. Okay, so first thing I'm going to do is I'm going to subtract Py from both sides. So we have dy dx is equal to minus Py. Okay. Let's separate the variables. And so I'm going to divide both sides by y. Okay. So you have 1 over y dy dx is equal to minus P. Okay. Let's integrate this. There's new noises every day coming from the brain groups. Okay, so on the left-hand side, we have integral of 1 over y, so that's just going to be natural logarithm of y. Right-hand side, we know P is just a constant, and so we integrate this, that's going to be minus Px. Okay. All right, we get out a plus C. For this case, it doesn't matter too much. We're just looking at this for inspiration. Okay. Let's raise both sides to the let's exponentiate both sides, okay, to isolate the y. And so what we get is y is equal to, so we have e to the minus px plus c. The e to the c here is just going to become another constant. And so that just multiplies out in front, a e to the minus px. Okay. So what do we notice about this function? So we notice right away that this is an exponential function. Right? So, if we get an exponential solution to a first order equation with constant coefficients, then, if we make kind of a leap in logic, or, maybe 2 or 3 leaps in logic, we can say that, if we have constant coefficients for the second order equation, what if our solution also was an exponential function? It's just moving furniture for functions. Okay, so let's try that. So let's come back to our second order equation here, right? And let's plug in a certain function here. Okay. So let's write our second order equation here, d squared y dx squared plus p dy dx plus qy is equal to 0. Okay. Remember, for any differential equation, we can always take a solution and just simply plug it in. Okay. So let's plug in. Let's plug in y is equal to e, and let's give it a generic exponential coefficient. We'll say y is equal to lambda times x. Okay. So I'm using the Greek symbol lambda here to represent just some constant, but you're going to see that lambda will have a purpose. Okay. Okay, so to plug it in, we have to take its derivatives, and so let's take dy dx, and so that's just to be lambda e to the lambda x. And then d squared y dx squared, second derivative, that's going to be lambda squared e to the lambda x. Okay. And what you're going to see is that this exponential form is actually going to work out pretty nice for us, because when you take the derivative of an exponential function, you just get the exponential function right. Okay. Okay, so let's plug in. Okay, so first we have d squared y dx squared. We just computed that, so that's lambda squared e to the lambda x. Plus p times dy dx, and so that's p lambda e to the lambda x plus qy, so that's q e to the lambda x, all equal to 0. Okay. We see that in every single term here, all three of them, we have e to the lambda x, and so let's go ahead and cancel that out. So we're going to factor it out and just divide by both sides. Okay. And so what we're left with after that is lambda squared plus p lambda plus q is equal to 0. Okay. And then we'll pause here, because what we have, instead of a differential equation now, what we have here is a quadratic equation for this solution lambda. Okay. And just like we defined above, this right here is our characteristic equation. All right, any questions on how we got to this point here? It's on the other side. Okay. All right, so this is great because we have your quadratic equation, right? One thing that you know about a quadratic equation is that there are two roots to the quadratic equation. Okay? Right? And so eventually we're going to be able to factor this into a form lambda plus lambda 1 multiplied by lambda plus lambda 2 is equal to 0. Okay. Where our two roots are lambda 1, lambda 2, or I guess specifically in this case, it's minus lambda 1 minus lambda 2. Okay. And so if we take those two roots and then we apply them to our solution, that's going to give us the two solutions that we need. Okay. And so we can form y1 of x. This is going to be equal to e to the minus lambda 1 x, and y2 of x is equal to e to the minus lambda 2 x. Okay. So this is great, right? And so we have our second order ODE. We get two roots of the characteristic equation. Those two roots of the characteristic equation is going to give us two solutions, right? And as long as lambda 1 and lambda 2 are different, then we're going to have two linearly independent solutions, right? So this works out great. And so this here kind of forms our basis for our solutions. So let me give you the quadratic equation just to kind of refresh your memory. Sometimes the characteristic equation, the roots will be fairly obvious, and so you can just factor it in your head, and that's fine. But if you need to use the formula, no shame in using the formula. I have to use the formula almost every time because I'm not that good at factoring. Okay, so the quadratic formula for this one is going to be minus p plus or minus square root of p squared minus 4q all divided by 2. Okay. And so this is going to give us lambda 1 and lambda 2. Okay, depending on if you're adding the radical term or you're subtracting the radical term. Okay, any questions on this before we do an example? Okay, all right, let's do an example, just so you can see how it all comes together. Okay, so let's look at the equation, d squared y dx squared plus dy dx minus 2y is equal to 0. Okay. And let's give it some initial conditions. And so we'll say y of 0 is equal to 4. And then dy dx at x is equal to 0. That's going to be equal to minus 5. Okay. So we want to solve for the full solution to this problem because we have the initial conditions. Okay. So whenever you have a second order equation with constant coefficients, the first thing that you need to do is to form the characteristic equation. Okay. So to form the characteristic equation, you're going to just use the same coefficients as the original second order differential equation, except you're going to replace every derivative with a polynomial tau. Okay. All right, so for instance, and so for this one, we have d squared y dx squared. That's going to become lambda squared. Okay. We have dy dx, that's going to just become a positive 1 lambda. And then we have a minus 2y, and that's just going to become minus 2. Okay. Right. So you're taking all the same coefficients, it's just you're forming a quadratic equation instead of the differential equation. Okay. So after you form the characteristic equation, you're going to compute the roots of the characteristic equation. Okay. So I'm going to go ahead and use my quadratic formula here. So we're going to say lambda 1, comma, lambda 2 is equal to, we have minus p, so we have minus 1 plus or minus square root 1 squared minus 4 times q. So q here is minus 2, all divided by 2. Okay. Okay, so let's go ahead and evaluate this. And so underneath the radical, we have 1 minus 4 times minus 2. 4 times minus 2 is minus 8. We have 1 minus minus 8. That is a positive 9. Okay, so you have minus 1 plus or minus square root of 9 divided by 2. 9 just happens to be a perfect square. And so taking the square root of that is going to give us 3. So you have minus 1 plus or minus 3 divided by 2. Okay. And so we perform the arithmetic. And so let's do the plus side first. We have minus 1 plus 3. So that's going to be a positive 2 divided by 2. So that's going to give us 1. Okay. So that's one of the roots. So one of the roots is 1. Okay. And then the other root here is a minus 1 minus 3 divided by 2. That's going to be minus 4 divided by 2. That's minus 2. Okay. So that means our characteristic equation here can be factored. So we have a lambda minus 1 multiplied by lambda plus 2. Okay. Where our roots, lambda 1 is equal to 1, lambda 2 is equal to minus 2. All right, any questions on how we got those two roots there? Okay, good. All right, so after you form the roots of the characteristic equation, you can go ahead and form your general solution. Okay. We have y1 is equal to e to the lambda 1 x, and y2 is equal to e to the lambda 2 x. Okay. So let's go ahead and plug in for that. So y1 of x is equal to e to the x, and y2 of x is equal to e to the minus 2x. Okay. All right, so let's take these two and let's combine them together to form our general solution. Right, and so to form our general solution, all we're going to do is we're going to take a linear combination of both y1 and y2. And so that means we're going to multiply them by an arbitrary coefficient for both of them, and then just add them together. Okay. And so y of x is equal to c1 e to the x plus c2 e to the minus 2x. Okay. And so if your problem just asks you to find the general solution, you can stop here. But if you're given initial conditions like we have in this problem, we need to take this one step through. Okay. But any questions on this up to this point? Our question from the chat. So by any chance, are we going to deal with imaginary numbers too, or do those even exist in real life engineering applications? We are going to deal with imaginary numbers. So we are going to deal with complex roots. That's going to be later on in the class. And to kind of quickly answer your question, when you have complex roots, that's when you have an oscillating solution. So your solution is going to vibrate basically. So any kind of engineering application that involves vibrations, in those cases, you're dealing with complex roots. Yeah, so it is actually very, very common. Yep. Okay. So now that we have the general solution, let's go ahead and form our full solution. So let's apply our initial conditions. Okay. And so our initial conditions in this case is y of 0 is equal to 4. Okay. So let's start with that one. Okay. So we're going to plug in x is equal to 0 here and set it equal to 4. So you have C1 times e to the 0 plus C2 e to the 0. And so that just gives us C1 plus C2 is equal to 4. Okay. So we have two unknowns right now. So we can't use this equation by itself to solve for one of the unknowns. So let's bring in the other initial condition as well. So our other initial condition is dx dy dx at x is equal to 0 is equal to minus 5. Okay. So to apply this boundary condition, we just need to take the derivative of our equation here. So you have C1, derivative of e to the x is just e to the x, okay, plus C2 times derivative of e to the minus 2x, and so that's going to be C2 times minus 2 e to the minus 2x, okay. Let's plug in x is equal to 0 because this is the derivative at x equals 0. So we have C1 minus 2C2, okay, is equal to minus 5. Right. Okay, so now we have two linear equations for two unknowns. Okay, so first we have C1 plus C2 is equal to 4, and then C1 minus 2C2 is equal to minus 5. So we can solve these equations for C1 and C2. Okay. Okay. So you can solve this, whichever way that you want. One trick that I like to use is I notice in both of these equations, we have a positive C1. So we have a positive C1 here, positive C1 here. Okay. So one thing I like to do is I like to what I call subtract the two equations. Okay. And so if you list the two equations on top of each other, C1 plus C2 is equal to 4, and then C1 minus 2C2 is equal to minus 5. Okay. And so if you subtract these two equations from each other, we have C1 minus C1, and so that's going to cancel out. Okay. Then we have C2 minus two C2, so that's the two net minuses are gonna cancel out, and so we have a three C2 on the left-hand side. And then on the right-hand side, we have 4 minus 5, and so that's gonna be 4 plus 5, which is 9. And so that gives us a solution for C2. So C2 is simply just 9 divided by 3, which is 3. Oops. C2. Okay. So that's how I like to solve these problems. Another way that you can do this is you can solve one equation for C1, substitute that into the second equation to solve for C2. That's perfectly fine too. So whichever your favorite way to solve for these linear equations, that's up to you. But the way at least I learned it more than 12 years ago is just to subtract the equation. So I do that, but don't feel like. Okay, so let's plug this back in and solve for C1. So now that we have C2 is equal to 3, let me go ahead and plug it back into the first equation here. Okay. And so we have C1 plus 3 is equal to 4. So this tells us that C1 is equal to 1. Okay. And so from that, we can form our final solution here. We have y of x is equal to C1, which is 1, multiplied by e to the x. Okay. Plus C2 times e to the minus 2x. So it's going to be a plus 3 e to the 2 minus 2x. All right. Any questions on this example here? Have we got everything? Okay, cool. So this situation here, let's back up a bit before we move on to the next example. In this example here, we had two roots to our characteristic equation, and they were both real numbers. Okay. So this is a case that we usually call in these equations called two real roots. Okay. So two real roots, this is probably the simplest case that we have. And when you have two real roots, your solution just ends up being two exponential functions. Okay. So pretty straightforward. That is the best case scenario, yes, or the fastest. Let's do another example. Let's see what happens when this is not the case. Okay. Okay, so for this example here, let's solve the equation d squared y dx squared plus 6 dy dx plus 9 is equal to 0. And in this case, we just did an example where we had initial conditions. So for this one, let's just find the general solution. Okay. So let's follow the same procedure that we did in the last problem. So step one, let's form our characteristic equation. So once again, we're going to form a quadratic equation, and we're going to use the same coefficients as our differential equation. Okay. So we have for this equation here, we have lambda squared plus 6 lambda plus 9 is equal to 0. Okay. Okay. Next, let's find the roots of the characteristic equation. So let's just use our quadratic formula once again. And so we have lambda 1 comma lambda 2 is equal to minus 6 plus or minus square root. We have 6 squared minus 4 times 9, all divided by 2. Okay. Inside the radical there, we have 6 squared minus 4 times 9, so that's 36 minus 36, and so the radical actually ends up being 0. And so our only root here is actually minus 3. Okay. In fact, this is what we call a repeated root. Okay. And so mathematically, if you were to reform this, it would look like the following. So we have lambda plus 3 quantity squared is equal to 0. Right? We have just one root of the characteristic equation. It just ends up being repeated. Okay. All right. So let's go ahead and let's form our general solution from the root. Just 1 in this case. Okay. And so we have a root of minus 3, and we have another root of minus 3. And so what that tells us is that y1 is equal to e to the minus 3x, and y2, same root, is e to the minus 3x. All right, but here is our problem, because remember, one of the requirements for our solutions to our second order ODE is that they have to be linearly independent from each other, right? Let's look at these two functions. It's really only one function. It's just, one function, just slap a 2 in front of it. Okay? So these two functions are the same. And so the same function is not linearly independent from each other. So that's bad. And so, through our characteristic equation, we were able to get two solutions. But it's just the same solution. One is just wearing a trench coat, right? So, just putting on a trench coat doesn't make you any different. And so we have a problem here. So we can't form two independent solutions from our characteristic equation. Okay. But we only have one root. And so it's not like we can come up with a different root without changing the original equation itself. And so we need to make one of these equations, we need to modify it slightly so that they are independent of each other. Okay. So we're going to use a technique here. And so the technique is called reduction of order. So there's actually a proof to this. It's kind of a lengthy proof, or not the shortest proof in the world. But basically, the result is actually kind of funny. So the result is that if you have two functions that are basically the same, functionally the same function, you can make one independent from the other without changing the solution by simply just multiplying by x. So that's probably how you learned it in your previous math class. And so this trick just ends up being called the multiply by x trick. So we're not going to go through the derivation. We're not going to go through the proof just because of time. But the proof actually is in the notes. So, by multiplying by x, we can take y2 and multiply that one by x, and that's going to give us two solutions without changing our roots. Okay. And so then if we do that, we get y1 of x is equal to e to the minus 3x, and y2 is equal to x e to the minus 3x. Okay. So our root is the same, and so we didn't change the exponent at all, and so they're minus 3 in both cases. But in order to make y2 linearly independent from y1, all we did was we just multiplied it by x. Okay. Okay. So now we have two linearly independent solutions that still obey, that still follow the roots of the characteristic equation. Let's combine them together to form our general solution. And so when we combine these together, we get y of x is equal to c1 times y1. So we have c1 times e to the minus 3x plus c2 times y2, which is x e to the minus 3x. So this example here represents another kind of very common case for the characteristic equation. If you have a repeated root, you need to multiply one of your solutions by x. All right, any questions on this case here? Okay. So that's two of our cases so far. So, ideally, when you solve your characteristic equation, you're going to get two distinct real roots. Then your solution is just you just form the exponentials and you form your solution that way. Case two, not so bad. So case two, let's say you have a repeated root. And so in that case, you just multiply one of your solutions by x, and then you have two distinct solutions from there. Okay. There is one more situation. In fact, Joel already kind of knows what it is, and I'm sure probably a lot of you already know what it is. And so those are cases when you have imaginary roots or complex roots. Okay. Okay. So just like before, let's do this with an example. Okay. So once again, for this problem here, we're just going to solve for the general solution. And so in this case, we have d squared y dx squared plus 0.4 dy dx plus 9.04 y equal to 0. So we have some decimals here. So this is kind of what you can expect when you're applying these equations to realistic systems. So, realistic, springs and circuits and stuff, they don't care about your whole numbers. They're going to have properties with whatever they are. So a lot of times those are decimals. Okay. So let's find the general solution to this. So once again, let's start. So let's start by forming the characteristic equation. Okay. And so for this case, it's going to be lambda squared plus 0.4 lambda plus 9.04 equal to 0. All right, step 2. Let's find the roots of the characteristic equation. So let's use once again our quadratic formula. Again, if you can find roots without the characteristic equation, or excuse me, without the quadratic formula, be my guest. Okay. So you have lambda 1 comma lambda 2 is equal to minus 0.4 plus or minus square root 0.4 squared minus 4 times 9.04. Okay. All divided by 2. You may need your calculator punch to evaluate the things on the radical. But luckily for me, I have the magic of I did this problem 4 years ago, so I know the solution already. So let me just go ahead and compute those. Okay, so 0.4 squared is 0.16. 4 times 9.04 is 36.16. Okay. All divided by 2. So you have 0.16 minus 36.16. That's going to be a minus 36. Okay. That's a negative number. So you take a square root of a negative number, that's always going to give you imaginary. Okay. And so when you evaluate this is going to be minus 0.4 plus or minus. Square root of minus 36 is going to be 6i. Okay. All divided by 2. And so when you divide this by 2, you get minus 0.2 plus or minus 3i. Okay. First, it was a furniture moving party. Now it's a party party. Okay. Any questions on how we got these roots here? Okay, good. Okay, step 3. Let's form our two solutions. And so in this case, we have y1 of x is equal to e to the minus 0.2 plus 3i x, and y2 of x is equal to e to the minus 0.2 minus 3i times x. Okay. So let's combine these together. So when you combine these together, we get a y of x is equal to c1 times e to the minus 0.2 plus 3i quantity multiplied by x plus c2 e to the minus 0.2 minus 3i times X. Okay. Technically, that's the solution. So you can just kind of leave it at that, but whenever you have imaginary numbers in your solution, it's always not very satisfying, I guess you kind of say it this. Okay. And so of course we want to put this in another form, a form that's a bit more palatable, or at least one that gets rid of the I. And so we'll do that in a second. Okay. Okay. So to get rid of the imaginary numbers here, we need to make use of something called Euler's formula. Okay. So it's actually really nice that our solution here is an exponential, because we do have a formula for an exponential of an imaginary number. Okay. So we're going to use Euler's formula, and then we're going to combine it with the fact that C1 and C2 here are arbitrary. Right now, they're still arbitrary constants. Okay. So what is Euler's formula? So Euler's formula is, if you take E raised to the I omega t. Okay. So in other words, you have an exponential with an imaginary number in the exponential. What this is equal to is cosine of omega t plus I sine of omega t. Okay. So in other words, you can use sine and cosine to represent that complex exponential. Okay. Okay. So let's take this formula and let's apply it to our terms up here. So we have a complex exponential here, complex exponential here. Okay. But before I do that, we do actually have a real part to this complex exponential. We have the e to the minus 0.2 times x. So first thing I'm going to do is I'm going to factor that out first. Okay. Let's factor that out, because that's not going to participate in this complex exponential thing. Okay. And so we have y of x is equal to e to the minus 0.2 x multiplied by c1 e to the 3I plus c2 e to the minus 3I. Okay. C3ix. So minus 3ix and minus 3ix. Okay. Now that we have in this form, we can just go ahead and directly apply Euler's formula to the e to the 3ix and the e to the minus 3ix. Okay. Okay. So what we're going to do is we're going to replace this with Euler's formula and this with Euler's formula. Okay. Okay. But first we have the e to the minus 0.2x. That one's still coming down. Okay. Then we have C1 multiplied by quantity cosine of 3x plus I sine of 3x. Okay. Plus C2. And then we're going to apply Euler's form to e to the minus 3ix. Okay. So that's C2 multiplied by quantity cosine minus 3x plus I sine minus 3x. Okay. All right, any questions on that so far? Okay. 15 more minutes. Okay. All right. I want to get through this at least. We'll probably do the mass damper stuff next time. But let's simplify this a bit first. Okay. So we have these minus signs within the argument of the sines and cosines, right? Let's make use of the fact that cosine is an even function. Okay. And so what that means is that if we have cosine of minus x, that's just going to be cosine of x. Okay. That's because, when you reflect the cosine function across the y-axis, you just end up getting the same function, right? It's reflective across that axis. And so that helps us. And so instead of cosine minus 3x, we can just replace this with cosine 3x. Okay. On the flip side, we have sine of minus 3x. And so once again, we have that minus sign within the argument of the sine. So we want to kind of, move it or kind of do something with it. Okay. And so on the other hand, sine is an odd function, right? And so when you take a minus argument of that, so we have sine of minus x, that's going to give us minus sine of x, okay? So the minus sign kind of moves out in front. And an odd function, all that means is that the function is reflective, or a function is, reflective about the origin. Okay? And so when you plug in a negative argument, it actually flips the sign of the entire function itself. Okay? And so that means when we apply this, what we get, instead of sine of minus 3x, we get minus sine of 3x. Okay. And so we did this just so that we can combine the sines and cosines from the second term together with the first one. Okay, so let's go ahead and apply those changes there. And so let me go ahead and bring down the e to the minus 0.2x. Then we have C1 cosine of 3x plus I sine of 3x plus C2. Here's where we're going to apply our even and odd functions here. So we have C2 times cosine of 3x minus I sine of 3x. Any questions on how we did that step there? Okay. All right, we're almost there. Okay, so now next step, let's now that we've changed everything to cosine 3x, sine 3x, let's combine all like terms for sine and cosine. Okay. All right, so if we combine like terms there, we get e to the minus 0.2x times, for cosine x, we get C1 plus C2 cosine 3x. Okay. And then for sine here, we get C1 times I minus C2 times I sine of 3x. Okay. Right. So this is really good because remember C1, C2 at this point, we haven't decided what their values are yet. So they're still arbitrary. And so what that means is that, we can kind of replace them with new constants, right? And so if we replace this with a constant, I'm tempted to just call it C1, C2 again, but we'll call this constant C1 plus C2, we'll call it A, okay? And here's the part here where you're gonna feel like I'm kind of cheating a little bit. The imaginary number, technically is also a constant. It's a very weird constant, and so theoretically it doesn't exist. That's why we call it imaginary. But it's still a constant nonetheless. And so we can actually replace this. We can kind of sweep the imaginary part under the rug, and we just call that constant t. Okay. And so our general solution, finally, after all these steps, is e to the minus 0.2x multiplied by a cosine of 3x plus b sine 3x. All right, any questions on how we got that that result there? Okay, I'm gonna yell at them. We're back. All right. Sorry about that. Okay. So this is our third case for when we have our characteristic equation, when we have we call these complex conjugate roots. Okay. So when you have complex conjugate roots, you have an imaginary number as part of the of your roots. You're going to get a sinusoidal solution, right? Now, do you have to go through this whole derivation or to plug in Euler's formula for every problem like this? No. So I only did that for the first time here just to kind of illustrate to you where these sines and cosines come from. Okay. And so when you have complex conjugate roots, here's kind of what I recommend that you do. When we get complex conjugate roots, you're going to have a real part to the root, and you're going to have an imaginary part to the root. So let me do it like this. So we have lambda1, lambda2 is equal to, okay? We have some real part. So we'll call it a plus or minus b times I. So that a there is the real part. And this b here is the imaginary part. And so once you kind of get to this point right here where you have the real and imaginary parts, you can just kind of plug that into your solution. Because what's going to happen is that the real part of your roots here is going to become the exponential part of your solution. Okay. And the imaginary part here, that's going to become the sinusoidal part of your solution. Okay. And so once you get this, your solution could be formed like the following. So you have y of x is equal to, okay. First you have the real part, and so we have e to the a times x. Okay. So that's the real part there. So that forms an exponential just fine. So there's no need for Euler's formula for that. Okay. And then the imaginary part will become the argument within the sine and cosine. Okay. So you need to have both. You need to have both sine and cosine there. So you have a cosine of b times x plus b sine of little b times x. Okay. So this b here goes right here, goes right here. All right, so that's what I recommend that you do. So, don't go through the whole derivation with Euler's formula and plugging in, and all that stuff. I would just jump straight. Okay. Okay. Any questions on this? All right. So when you do have these types of solutions here, very commonly this real part is going to be negative for most situations. So this a here is going to be usually negative. Okay. And by usually, I mean it should be negative. If you don't have a negative real part, then something probably went totally wrong, or you're living in a simulation. But we might be living in a simulation right now. Okay. So what that means, and so if you look at our previous example here, right, we have that exact case, and so our real part here is actually a minus 0.2x. Okay. If you remember our discussion from last time, so last time we talked about this idea of a transient part of the solution. Transient meaning that, as x increases in value, then that part's going to decay down to 0. Okay. And so that's true here as well. And so we have a decaying exponential here. That tells us that this entire solution here is going to decay down to 0. But it's also going to oscillate at the same time. Right? And so when you have a situation like this, so when you have complex conjugate roots and the real part is negative, okay, this is a very particular case which we call damped oscillations. Okay. And so when you plot it, it looks like the following. So we have, okay, like this. You might start with oscillations that are fairly large, like this. Okay. But eventually, the magnitudes of those oscillations are going to go down to 0. Okay. And so if you kind of draw an envelope here, so you kind of draw kind of a sheet over the magnitudes of the oscillations, you can see that eventually the magnitudes are going to go down to 0. So that right there is a very common case, and kind of forms the basis of the entire course of vibrations. So for those of you who are in ME, the class that you're going to take after 308 is called EGME 431. So that's all about vibrations. So this idea of having, second order systems that are governed by second order ODEs that are going to vibrate, they're going to oscillate up and down, but eventually their magnitudes are going to decay down to 0 because of some natural damping, because of friction within the system itself. Okay. And so when we come back to class on Tuesday, we'll explore this application a bit more. And so we're going to talk more specifically about the mass spring damper. We're going to talk about its applications within engineering, and just all the different types of things that it can apply to. Specifically, the shock absorbers in the pump. Okay. And hopefully on Tuesday, I won't have to yell at them again. So hopefully it's quiet stuff. So thank you guys for coming today. Thank you guys for your patience with all the noise next door. Hopefully we'll start an issue next week. Hope you guys have a good weekend, and I will see you on Tuesday. Yeah.
Bye, thank you.
Yeah, thank you.
I didn't get it. Yeah, I heard that. Let me know, tomorrow. So we didn't have access to cameras after they do day for honors.
You can still submit. Yeah,
Okay.
yeah, I was gonna talk to you at some point, yeah, go in, because you joined late, so yeah,
Right.
just send me an email and I'll give you.
Got it. All right.
Yep, mhm.
Thank you.
Yep, have a good weekend. All right, David, Gerardo, any final questions before I close up the Zoom?
Yeah, my bad. I was just waiting. Sorry about that.
Oh, sorry, Gerard, are you, hang on, I think the volume's off. I do see
Okay.
that your mic, you are speaking though. Try the volume here. All right, try again.
Wait, can you hear me?
Hang on, the volume's still not working right now. Can you type your questions? Sorry. Yeah, I don't think there's a sound system in this room. I mean, that's why. Oh, okay. Yeah. So yeah, there was a typo on 2A. Yeah. So it should be a minus. I don't know if you got that at the beginning. Oh, problem 4. Okay. Let me bring up problem 4. So problem 4 is a separation of variables problem. Let me see if I can bring it up. Screen. All right. So this one, right? Okay. Yeah, so first thing you should note here is that when you look at the equation itself, you have I to the 2/7 power. So that's a nonlinear term. So this one, the only way that you can solve it is with separation of variables. And so the way to do this, I don't know if I can draw on this. Actually, let me bring back my iPad here. Okay, so we have di dt is equal to minus 14I to the 2/7, right? We see right away that that the 2/7 here makes this equation nonlinear. Okay. So the only way that we can solve it is by separating the variables. And so what I'm going to do is I'm going to divide both sides by I to the 2/7. Okay. Effectively, what that's going to do is going to take I and move it to the left-hand side of the equation. Okay. And so so we have I, and since we have I in the denominator here, I'm just going to raise it to the negative power. So we have I to the minus 2/7 di. Okay. And then on the right-hand side, I'm going to take the dt and move it over there since we're separating the variables. So we have minus 14 dt. Okay. Let's integrate this. And so when we integrate that left-hand side, we're going to add 1. We're going to do basically the antiderivative here. So we're going to add 1 to the exponent. So we're going to have minus 2/7. So we have I, the minus 2/7 plus 1. So plus 7/7. And so that's going to give us I to the 5/7. Okay. And then we have to take the opposite of that too. So that's going to be 7/5. Right? So this term comes out just from the antiderivative, because if we take derivative of I to the 5/7, we get 5/7 I to the -2/7. So this one comes out here. I guess you can call it power, opposite power. Excuse me. And on the right-hand side, we have minus 14. Minus 14 is just a constant, so we just integrate, we get minus 14t plus c. Okay. Okay. And then to isolate I here, we're going to multiply both sides by 5/7. Because we have I to the 5/7 is equal to 5/7. So I'm basically just taking this term and dividing it by that side. Times minus 14t plus c. Okay. That's going to be I to the 5/7 is equal to minus 10t plus c. Okay. The c there is arbitrary, and so we can just leave it. We can just leave it as c for now. And then to isolate I, basically to cancel out the exponent of 5/7, we're going to raise both sides to 7/5. And so that's where that exponent kind of comes from. Okay. Does that make sense? How we do everything here? Okay, good. All right, I have to run to my next class, but if you have any more questions, just shoot me an email. Okay. All right. Have a good weekend.